The next talk is by Chi-Kang Chang, and it will be about Corti's inequality and birational rigidity. Please.
Okay. Thank you for the introduction. Also, I'm also an algebraic geometer. So today we'll talk about Corti's inequality and birational rigidity. Okay. This talk is based on a joint work with Chen Zhenjie and Takuzo Okada. And if we does not specify, then every variety are assumed over the complex number field C. Okay. At first, I will give a quick review about algebraic geometry and birational geometry. The definition of algebraic variety is the zero locus of a polynomial function. For example, the zero locus of x minus y is a line. The diagonal on the plane, and the zero locus of x squared plus y squared plus y squared minus z squared is a cone. And the zero locus of the set of the two polynomials, x squared minus y, x minus z, is a parabola. In the projective space, the zero locus of the polynomial x squared plus y squared equal to z squared is a circle. And the curve y equal to sine x is not an algebraic variety because the defining equation is the sine function, not a polynomial. For example, the red guy is the parabola, it is algebraic. And the blue guy, the cusp curve, a singular elliptic curve, is also algebraic. But the sine curve, black guy, is not algebraic. Algebraic geometry is the mathematical branch that study geometry property of algebraic varieties. We say two algebraic varieties are isomorphic if they share the same structure as algebraic varieties. For example, the parabola and the x-axis is isomorphic, and the notation is this. We write this notation as isomorphism. For example, the parabola to the line is an isomorphism because it is 1, 1 and onto and does not change the algebraic geometry property. This is smooth to smooth, 1 to 1 and onto. So in algebraic sense, they are isomorphic. In this set, here, the line and the cusp curve is not isomorphic because although there is a 1 by 1, 1 to 1 and onto map, a set, but here is the line is smooth, but the cusp has a singularity. So although there is a one bijective set map between set, but as algebraic variety, they are not isomorphic. Also, the line is also not isomorphic to the nodal curve because the node has two preimage. There are 2 points will send to the same node. This map is not bijective, so actually not isomorphic. A question in algebraic geometry is how to classify algebraic varieties. If we want to classify all algebraic variety, then it is much variety to classify. So it is quite different. On the other hand, if we regard variety with almost isomorphic global structure into one classes, then the classification problem will be more feasible. So this is the motivation of birational geometry. We say two algebraic varieties are birational equivalent if they have open dense subsets that are isomorphic, and the notation is that. For example, the complex plane and the sphere are birational equivalent. Cone and the cylinder are birational equivalent. Smooth compact Riemann surface with different genus are not birational equivalent. Okay. For example, they are all birational equivalent because if we removing the node here, if we remove a point on the line and remove the node of the cusp curve, remove the singularity of the cusp curve, then the remain is a 1, 1 onto map between smooth guys. Also, if here we remove the 2 point and here remove the node, then the remain guys is also 1, 1 onto between smooth guys. Okay, for example, also here is like the picture to explain why sphere and the plane are birational equivalent. As you see, if we remove the north pole and we take a light from north pole to project the sphere to the plane, then the map from the sphere to sphere remove north pole to the plane is 1, 1 on 2. You can see the yellow point to the yellow point, the red point to the red point, the blue to the blue. This is a 1 to 1 and onto morphism. And after we remove the north pole, so this is an example to see that two smooth guys is also could be not birational, could be non-isomorphic but birational equivalent. Okay. Also, if in case the singularity is very bad, two birational equivalent varieties can be quite different in the global structure. You can see in the cone to the cylinder to the cone, if we send the red line to the red line, the yellow line to the yellow line, blue to blue, green to green, then we can see that this map, if we remove a circle from the cylinder and remove the node from cone, then the remain parts are 1 to 1 and onto. So although the cylinder and the cone globally looks very different, but they are isomorphic. They are birational equivalent. Actually, such thing only happens when there is a very bad singularity. And also, this is another example of non-isomorphic birational map. This is a singularity. This is the above is the usual plane, and this guy is a singular surface. This point is this guy is defined by the equation. This singularity is usually called A1 singularity. This you can see. This is also a 1, 1 onto map as set, but since this is smooth, this is singular. They are not isomorphic. But after removing a point and removing the singular point, the remaining guys are isomorphic to each other. So it is also an birational map. On the other hand, you can for the Riemann surface, if the genus is not different, they are not birational to each other. In fact, for a smooth Riemann surface or complex projective curve, they are equivalent. Two complex projective smooth Riemann surfaces are birational equivalent if and only if the genus is the same. Also, in fact, if smooth and with the same genus, then they are all diffeomorphic. However, because we regard in algebraic geometry, we not only regard the geometry structure but also algebraic structure. So two torus can be, every torus are always diffeomorphic as differentiable manifold, but it is possible two genus are not isomorphic as algebraic varieties. And one important, maybe not one, this is the combination of two theorems from Zhou Weiliang and Heisuke Hironaka. The theorem is that every algebraic variety over the complex number is always birational equivalent to a smooth projective varieties. Smooth projective means it is a subset of projective space. Also, a question is, in a birational equivalent class, how to find a good representative variety of this class? This is the minimal model program. Okay. So we give some definitions. For a projective varieties with only mild singularity, that is, in fact, what singularity is mild is another question. But in this talk, we say mild means the singularity is not so bad in some algebraic geometry sense. Okay, if we collecting all top differential form on on a projective variety, then all the set of all top differential form will form a invertible sheaf. And the invertible sheaf can be associated and line bundle. This is a canonical one-to-one corresponding in algebraic geometry. And the line bundle comes from the sheaf of top differential form. It's called a canonical bundle. And we can define the dual bundle. The notation, the canonical bundle, the notation is OXKX. And the dual bundle OX minus KX is called the anti-canonical bundle of X. Okay. And the definition, there is some definition come from the minimal model program. We say a variety is minimal if the canonical bundle is NF. And NF is meaning numerically effective, come from numerically effective. This definition is a little difficult, a little complex, This definition is maybe not easy to explain without without language in algebraic geometry, but you can regard NF means the canonical line bundle is positive enough in some sense. On the other hand, we say a variety is final if the anti-canonical bundle is ample. Ample is also a notion from algebraic geometry. The meaning is the codila map. If we have from a line bundle, we can collect the global sections, and taking the basis of global section can give a map from the variety to the projective space. If the map is injective, then we say the line bundle is ample. Actually, although this is a little complicated, but at least final also means the anti-canonical bundle is very positive. So there are two. So also we say a variety is rational if it is birational equivalent to the projective space. For example, the projective space itself is actually final and rational. Also, in case the variety is a smooth irreducible hypersurface, hypersurface means this variety is defining by only only one polynomial. That is, it is the zero locus of a unique polynomial. In case of smooth irreducible hypersurface, this guy is minimal if the degree is at least n-1, or it's final if the degree is at most n. Okay. Yeah. So the conjecture, the minimal model program, this question is still a conjecture in higher dimension. For a projective variety with mild singularity, if the canonical bundle has non-negative codila dimension, then X is birational equivalent to a minimal model. Or if the line bundle have negative codila dimension, then there is a projective variety birational to X with mild singularity such that there is a morphism to another projective variety from Y to Z, and the fibers are final of Picard number 1. In the second case, we say this map is a multi-fiber space. Okay, some easy examples of multi-fiber space. For example, the projective space to a point is actually a multi-fiber space because projective space is final. Also, not only projective space, any final variety with mild singularity and Picard number 1, X, we always have X to a point is a multi-fiber space. Also, but for the product of two projective space, Pn cross Pn, we take the first projection to Pn, it is also a multi-fiber space. But in this case, if we direct send Pn cross Pm to a point, then it is not multi-fiber space. Because although it is final, but the Picard number is 2. Okay, and the definition of birational rigidity is that for a Picard number 1 final variety with only mild singularity, we say X is birationally rigid if there does not exist a modifiable space Y to Z such that Y is birational equivalent to X, but not isomorphic to X. That is, birational rigidity means in this birational class, X itself is the unique one modifiable space. Okay. So before explain why we need the notion of birational rigidity, at first we talk something about the rationality question. A question is, are all Fano varieties rational? The answer is, if the dimension is 1 or 2, then it is true. In dimension 1, the projective space, the sphere, that is the complex projective curve with genus 0, the sphere is the only one smooth Fano variety in dimension 1. In dimension 2, there is many Fano varieties, all of them called Delpezzo surface. But every Delpezzo surface are rational. So until dimension 2, all Fano guys are rational is true. However, after the dimension being at least 3, there appears non-rational Fano variety. Appears Fano varieties that is not rational. One example given by Clemens Griffiths is a smooth cubic threefolds. That is in P4. That is a hypersurface defined by a degree 3 polynomial. This is a non-rational Fano varieties. Okay. So another question is how to determine whether a variety is rational or not. So one approach is that given a rational variety with dimension at least 2, then because it is rational, by definition, it is birational equivalent to Pn. And also, Pn is birational equivalent to Pn minus 1 cross P1. Note that Pn to point and Pn minus 1 cross P1 to Pn minus 1 are both modifiable space. In particular, any rational variety with dimension at least 2 must birational equivalent to at least 2 different modifiable spaces. Therefore, a rational variety are always not birational rigid. And conversely, birational rigid Fano varieties are always non-rational. Hence, if we find a Fano variety which is birationally rigid, then we construct a new class of Fano variety that is not birational equivalent to projective space. Here are some examples. The P1, the rational curve, complex, and the sphere, it is birational rigid. But if n is at least 2, Pn are always not birational rigid. In particular, as we say, every Fano surface are rational. So there is no birationally rigid surface. So in dimension 1, every Fano are birationally rigid. But in dimension 2, every Fano are not birationally rigid. So the first non-trivial dimension is dimension 3. There are several examples given by Clemens, Griffiths, and Iskoviskik. For a smooth irreducible hypersurface of degree d in P4, if the degree is 1, then X is isomorphic to P3 because it is just a hyperplane in P4. If degree is 2, then X is a rational Fano variety, but not isomorphic to P3. If the degree is 3, then X is a Fano variety that is neither rational nor birationally rigid. If the degree is 4, then X is birationally rigid Fano threefold. And if the degree is at least 5, then X being not Fano. Therefore, in a naive sense, we may regard in the world of Fano variety, the projective space has the most positive anti-canonical bundle in the world of final varieties. And rational final varieties has stronger positivity of anti-canonical divisor than non-rational guys. Also, the birationally rigid final varieties has the least positivity of anti-canonical bundle in the world of final. So we may regard rigid means it is in some sense, it is the boundary of final, because it is the final varieties that has weakest positivity of anti-canonical bundle. Okay, from now on, here will appear some difficult things. From now on, there will appear many algebraic geometry languages. The Noether-Funnell inequality, the Noether-Funnell method and the Corti's inequality is that the Noether-Funnell method means that if a final variety of Picard number 1 is not birational rigid, then we always can find a mobile linear system in the in minus nkx, the anti-canonical bundle, twist n times, such that this pair x 1 over nm is not a canonical pair. Yeah, sorry, here is many notion in birational geometry. So, okay. So maybe regard it as a story if you first see them. If this is the first time for you see them. Also, and another important tool is the Corti's inequality. Today, if we are on a surface, and L is the mobile linear system on S such that the pair S 1 over mu L is not log canonical at a smooth point for some positive rational number, then for general members in this linear system, we have the local intersection multiplicity L1 intersects with L2 is at least 4 mu square. This is the famous Corti's 4 mu square inequality in algebraic geometry. And what is the relation between the two theories? Is that assume a final threefold of Picard number 1 has a smooth point that is a non-canonical center of such a mobile linear system. Assume such guy exists. Then we take a surface. Let's take S be a smooth hyperplane section passing through the point 0. Then we can see S plus 1 over mu m is not log canonical at the point 0. Then we using the adjunction formula restricts this linear system onto S. Then we can see S 1 over mu L is not log canonical. So applying Corti's inequality for general members, we have the intersection multiplicity is at least 4 mu square. Hence, hence assume such a point, such non-canonical center exists, then for any smooth irreducible hyperplane section, we always have the intersection number S dot minus kx squared is more than 4. Conversely, if S dot minus k squared, the intersection number is at not more than 4, then every smooth point on X are not a non-canonical center of such a mobile linear system. So in this case, if the intersection number is small enough, then we can see no smooth point are non-canonical center. So assume there is canonical center, it can only happen on either singular point or the center is a whole curve. Only these two possibilities. Okay, so now we talk about smooth points. A natural question is, could we generalize Corti's inequality to singular points? Okay, about this, maybe we can see the birational rigid result of some special varieties. For example, the theorem of Chelsoff and Park prove that a smooth sexty double solids are birationally rigid. Sexty double solid means it is a 2-to-1 cover over P3 and ramified over a degree 6 surface. Chelsoff and Park prove that smooth sexty double solids are birationally rigid, but Pemeru proved that if a sexty double solid contains a singularity that is in CAN type and the n is at least 4, then these sexty double solids are not birationally rigid. So it is usually regarded if a variety have a bad enough singularity, then it is more difficult to be birationally rigid. Okay. Here is also another theory to explain how to show a curve is not a canonical center, a non-canonical center, but we omit the details in this talk. Okay, so for singular point, one theorem is from, there are two works from Krylov, Okada, Pemeru, and Park. Their result is, for a CAN point, CAN singularity on a threefold, assume this CAN point is a non-canonical center of such the mobile linear system for the rational number. Then, for general members, the multiplicity of local intersection is at least 4 over n plus 1 mu. Also, in fact, smooth point can be regarded as a CA0 singularity. So this is coincide with the original formula square singularity inequality. And by this inequality, Krylov, Okada, Pemeru, and Park prove that Q factorial sexty double solid with only CA1 point, or factorial sexty double solid with only CA1 or ordinary CA2 singularities are birationally rigid. So if the singularity is mild enough, it is still possible. The singular final threefold could be birationally rigid. And this is our result. The result of me and Chang and Okada is that today, if we have a Duval singularity, Duval is a special type of surface singularity. And in the same setting of Corti's inequality, expect the point is not smooth, or the point is from smooth point being a Duval singularity. Then our result is we still have a similar inequality, but the coefficient will be weaker. If AN type, then it is 4 over n plus 1. If it is DN type, then the coefficient will be 1 over n minus 2. If it is E type, then E6, E7, E8 will be 1 over 6, 1 over 12, 1 over 30. Yeah. So for a singular point, we still have Corti type inequality, but the coefficient will be quite lesser. However, such inequality still exists. And applying a junction formula, we can from surface Duval singularity to threefold compound Duval singularity, and the coefficients are all the same as surface case. And our result is by this new inequality, we found there exists a birationally rigid final threefold with CD4 singularity. This is a singular weighted hypersurface of degree 18 in the weighted projective space P1, 2, 3, 4, 9. And this is the first example of birational rigid final threefold with CD type singularity. And the final remark is that all the inequality of singular point appear, no matter the original result of Krylov, Okada, Pemeru, Park, or our new result. All of them are optimal. That is, we prove that this inequality cannot be better. It is the the optimal result. Okay. Okay, so maybe I stop here. Thank you.
Thank you very much. Do you have any questions, comments?
Last equality, the rational number is optimal. You mean
Yes.
okay, I see. So you cannot. It's a kind of the largest rational number.
Yes.
For this.
That is, we can construct any example. For example, for CE6, we can construct examples that the multiplicity is 1/6 plus epsilon mu square, and the epsilon could be arbitrarily small in this sense.
Okay. And is there some meaning of that rational number, or it's a kind of a?
You say this number, the meaning of these numbers.
What number?
Yes, in fact, these numbers are important geometric meaning. That is, all Duval singularity is in fact can be regarded as a finite group quotient of a smooth point, and all of these numbers are the 4 dividing by the order of the quotient group. Yeah, this is the meaning of these coefficients. Okay.
Thank you very much.
Okay.
Thank you. Any other question or comment? Okay, then if not, let's thank Chi-Kang again.
Thank you.